Okay, so let's talk about O-rings for a bit. Over the years I've repaired many an O-ring groove. I've never really sat down and designed a setup from scratch. And luckily the internet is full of useful information we can use and help us design a setup for our water hose. So I found a place online, applerubber.com, and they have some online calculators and a whole bunch of design information that if you sit down and read it, it sheds a lot of light on it and helps you design a setup. And you can print it off and take your numbers, go make your part. Quite easy. So when we design an O-ring bore and grooves, all the dimensions are calculated to give you a good fit in your bore and to provide the right amount of compression on the O-ring. The three values that are important, of course, are the how much the O-ring is stretched when it's put in the groove. There is a certain amount you need to stretch it. 1 to 5% is your range. We're shooting for roughly 2. And then you have the amount of compression once it gets inserted into the bore, and that will range anywhere from 10 to 30%. We're going to shoot for somewhere in the middle. So our stainless material we're using is a 1-inch diameter. It actually mics out at a 1 thou over. So we're going to try to retain this size if we can. So that'll put our bore size in our brass part at slightly over 1 inch. You want a few thousandths in there, but not so much that it's too loose and the O-ring can squeeze out around the gap. Recommended clearance is roughly 5. Now the numbers I'm quoting are what I've calculated for this particular type of seal. It's a radial seal, and it's called an oscillating seal instead of a radial seal like a hydraulic rod, which slides sideways. So in this case the seal only has to rotate. We picked an O-ring out of our kit. It's a metric kit. It's all I had and I have here right now. And so I just converted all the numbers to standard to use in the online calculator. And it happened to work well with our dimensions of parts we have on hand here. So running the online calculator, we input a few values, and this is what we come up with. Our piston diameter we're going to leave the same as the material at 1 inch. To get clearance we're going to put our bore diameter at 1 inch and 4 thousandths. That's a little tight, but if I increase the bore diameter it drives some of the other specs out of whack, so we're going to give it a try. We can always remove material. It's a lot easier than putting it back in. Groove diameter to get the right amount of stretch on our O-ring winds up to be 13/16 or 0.8125. That gives us 3% stretch in the middle, and with the bore diameter we get we're in the middle range of compression at 18.8%. Other than the extrusion gap, which is your clearance on your piston to bore, we're well within spec on everything, so we're going to give this a try and see how it all works out. Let's get to cutting some metal. Not bad, 50. Let's get it dialed in. boring bar set up, and we'll do a bore for these O-rings. Alright, we're going to get ready and bore this. We got a nice fresh insert in the boring bar for a good finish. We're going to run in about 1 3/8 inches, so I'm going to mark my taper shank and free drill this first. Alright, let's get a nice true bore in there. We're going to find our bottom by hand here. Just about there. We'll set a 0. So we'll know where to stop. Better when you know where to stop. Okay, one more little cut and then we'll go get a better measuring tool. We'll break out our baby starts today. We're right there at 984. A little thumb pressure so we don't leave a drag mark, and now we'll check it again. Feels nice. We took another 5 then, by the way, so we're at 90. 990, we need 1 4 inches. So we're going to go right there at 13.5. And hope we don't overshoot too badly here. So, let's hope we didn't screw up too bad, because everybody hates it when you're video recording and you don't hit your numbers, right? Oh baby, that's 1 2 inches. Let's give it a spring cut, see what happens. Well, one of 1 7 inches probably. That's a spring cut. Probably that's what we're looking for. Oh, I didn't like the feel of that. Yeah, we're right there at 3.5. Let's check it again. Maybe even turn it 90 degrees here. Yeah, we're right there at 3.5. I should have dialed into 14 instead of the 13.5, right? I'm going to try just another small cut. I'd like to hit that 4 if I can, or maybe even 5. I don't mind being a thou over. Now we're right there at 4.5. Yeah, we're going to let her go at that. So we got our bore finalized, gave it a little polish with some Scotch-Brite. Actually, well, we did our taper first. We set our compound to 3 degrees, made a small lead-in taper that extends in about 3/16 of an inch to help give our O-rings a way to slide in easily without nicking on any corners, and we got our Scotch-Brite and rounded our corners off really nice. So this part is ready to go. Okay, so the plan here is to cut a couple of O-ring grooves and then part the part off. Now we have 1 3/8 inch depth in our brass section, so we'll mark this off roughly 1 3/8 inch, not a critical measurement at all. So we'll part it about there, and we'll run probably 2 O-ring grooves. I'm thinking at 1/4, and well, by the time we factor our width of groove, probably somewhere around 5/8. Yeah, let's even use the scale and try to get it close instead of just marking it. One 375. That'll be our part line. So we'll run down here at 1/4. Indicator to widen out our groove. Set a 0 there. Our groove is 146. The tool is 125. That's 21 off to the side. And I didn't set a 0 on my cross feed, which would have been prudent. So let's move down. We'll grab a new 0 here. That would be there. And to get to our 812.5, we take off 178. Right? Yeah. No, 180. Let me get it. Let's start out back at our 0. There we go. So that's 185. We leave a bit for finishing. Now we need to step it down, yeah, 21 thousandths, which is there. How's it looking? Okay, let's get some calipers in there and check our diameter.